Okay. So I'm going to talk about Spark time series, an open source time series library for Apache Spark 2.0. It was created and is being maintained by Sandy Riza, who is co-author of the book Advanced Analytics with Spark, Patterns for Learning from Data at Scale, and he's senior data scientist at Clover Health. The project was started in February 2015, so it's about 2 years old, and the API is still a work in progress. I'm Chief Data Science Officer at Fame Data. I've been a contributor to Spark time series for, well, since September 2015, and I've also participated in the early design discussions in March 2015. In addition to that, I've been an active user of the library for almost 2 years. So maybe a quick show of hands. Who uses time series right now in a project? Okay. So I'm going to go over some of the design questions we asked ourselves as we build the foundations for this library. And the first question is, how do we structure these multivariate time series? Do we go for a columnar representation or row-based representation? And what I mean by that, on the left, we have the columnar representation where the fundamental unit in your collection is a vector that represents all the values across time of a single variable. Whereas on the right, in the row-based representation, the fundamental unit in our collection represents the values of all variables at a single instant in time. So to make that choice between the two, we asked ourselves, what are some of the operations we're going to perform on these multivariate time series? And if we look at operations like time lagging, differencing, rolling operations like moving averages, feature generation, selection, transformation, those tend to be more efficient in columnar representation. Instead, if we look at things like machine learning algorithms like regression, clustering, classification, these tend to be more efficient in row-based representation. And let's take the example of lagging. So if our data structure is based on rows, what we have to do is we have to go through every single row, and for each row, we have to go back by some amount k, where k would be our selected lag amount, and copy over the relevant value. So even assuming that this collection is already pre-sorted chronologically, they're still going to have a time complexity of big O of n. On the other hand, if the data is columnar represented, all we have to do is truncate the most recent k values of the columns we're lagging, and then truncate the oldest k values of the global datetime index. And this will have the effect of lagging these columns relative to the other columns. And the time complexity of that operation is constant. So in this case, the columnar representation is being favored. But let's take a counterexample, a regression in a time series context. So what do we do in regression? Well, we have this parametric model here, and we're trying to forecast the variable y at some instant t as a function of other variables and lags of those variables. And one thing that's missing in this model here is also that we want to add potentially lags of y itself, but that's the general idea. And what we're trying to do is find these optimal beta coefficients that will provide the best predictions. And in a context like this, what we typically do is we pre-generate the lags of the variables as new columns in our data. So a single row will contain all the information necessary to make the predictions or the error calculations for a single example. So how do we find these optimal values of these beta coefficients? In most modern and scalable libraries, we use algorithms in the family of gradient descent. In particular, stochastic gradient descent is a popular choice. And what stochastic gradient descent does is it iterates on single examples to estimate the error gradient based on the current model, and then it adjusts the weights of the model based on that error gradient, and it keeps doing that until convergence. So what that means is that the fundamental unit of operation in this case is a row in our data rather than a column. But even if we go further than that, if we look at performance considerations and scalability considerations, when we calculate the error gradient for a row, we want all of the data in that row to be available locally on a single machine. We don't want to have to fetch that data on other machines, which is called shuffling, for the performance overhead that it incurs when you do that. So even if we look at performance, then we want to make sure that the partitioning is made such that all the data in a row is available locally on the machine. And for all these reasons, this is why the MLlib regression APIs, for example, are based on the concept of the labeled point, which is essentially a row in our data. Okay, so we've looked at the pros and cons, some things favoring columnar, some things favoring row-based. So what is our choice in this Spark time series library? Well, our choice is that the core representation is columnar, but we offer utility functions to go to and from row-based representation. And the reasoning behind that is that the scope of the operations that are made typically with Spark time series, things like differencing, lagging, and all that, tend to be more columnar efficient. Whereas the things that are more machine learning based and that are more row-based efficient tend to be done by other libraries like MLlib, for example. So the result is a typical time series analytics workflow with Spark time series looks something like this. So we load some data into a time series RDD, and then we apply all the necessary lags, differences, feature transformations with Spark time series within a columnar representation. Once we're done with this pre-processing, we call the .toInstance method on our time series RDD to transform to row-based representation. Once we have that, then we can use external libraries like MLlib or other statistical analysis libraries to do the rest of the analysis. Okay, another show of hands. Who uses univariate time series that don't fit inside a single executor's memory, or alternatively, multivariate time series where a single vector doesn't fit in the executor's memory? Okay, a couple, but a very small percentage. Okay, so the second design question that we asked ourselves, which is very much related to the first design question, is how do we partition these multivariate time series for distributed processing? So now we move from traditional algorithmic considerations to more Spark-related or distributed processing-related considerations. So do we partition this data set across features, or do we partition it across time? Our current solution is partitioning across features. And what that means essentially is that we have a datetime index that is sitting locally on the driver, and then we have our vectors that are distributed across the executors, and each vector is all of the values of a single variable across time. But the assumption behind that is that a single time series must fit inside your executor's memory. And this is what our time series RDD object looks like. So there's two components. There is the datetime index, which is an interface that has three implementations. There's the uniform datetime index for evenly spaced time series. There's the irregular datetime index for unevenly spaced time series. And there's the hybrid datetime index, which is a construction of one or more uniform and irregular datetime indices. And so if we go back to the time series RDD, we have the datetime index, and then we have the actual data, which is an RDD of a pair of k and vector, where k is an arbitrary identifier for this variable, and vector is all of the values of that variable across time. Now, if we look at the irregular datetime index object, we have an array of long values, where the long is the number of nanoseconds since epoch. So we have nanosecond precision in this library. But this library is written in Scala, and the arrays in Scala can support up to 2 to the 32 elements, which is about 4 billion. And 4 billion may seem like a lot, but in a big data context, it's not inconceivable to want more than that. So given those limitations that we've just talked about, we're already thinking about future improvements, an important one being that we would have another time series RDD-like class that would be partitioned across time rather than partitioned across features. And the result of that would be that you would have the two types of partitioning available on a case-by-case basis. Okay, the last design question, and then I'm going to go over the API and show some code examples. So this design question is, how do we apply differencing and lagging operations on our time series? Do we resample the data? Do we preserve the index? And this is what it looks like. So if we resample the data, we start with an irregular time index, and we end up with a uniform time index. In this example, it's a 1 second lag that we apply, so the resulting uniform time index is made of 1 second intervals. On the other hand, we can also apply this kind of operation where we start with an irregular time index, and we end up with the exact same irregular time index, except the values of the variables are lagged where appropriate. And to explain how the lagging works here, if we look at, let's say, the instant at 1 hour, 30 minutes, and 12 seconds, well, to get the lagged value of that, we have to look at 1 hour, 30 minutes, and 11 seconds. But there's no such entry in the date time index. So what we do in that case is we find the most recent value before that. So that would be the value 4.97, which is at the time 1 hour, 30 minutes, and 8.4 seconds. So this is why in the lagged data set, the instant 1 hour, 30 minutes, and 12 seconds has the value 4.97. Okay, so what is our implementation choice for that? Well, we provide both solutions. We have a resample function that allows resampling the data and perform operations like the first example that I showed. And what you do is you need to pass a custom aggregation function that will tell the algorithm what to do when you have multiple values that are being condensed into one. But there are some conceptual problems with using this in a machine learning or statistical analysis context. And the problem is that when downsampling occurs, there might be information loss. And where upsampling occurs, there might be duplication of values. And I will show that both of these situations occur in this first example here. If we look at the value at 1 hour, 30 minutes, and 7.86 seconds, the second one from the top, the Y value is 52.37. But in our uniform resampled data set, that value has completely disappeared as a result of the resampling process. So in other words, we just lost a data point, which is not so good for statistical analysis. And the other problem, if we look at the Y value 55.87 on the right, it's repeated 3 times. And that's also the result of upsampling. And if you think about the context, let's say financial trading, and you're building a forecasting model based on this transformed data, the model will be built on the impression that this stock was traded 3 times in 3 seconds at $55.87, right? So this is not really what happened. So there's some conceptual problems with doing this kind of resampling for the purpose of statistical analysis. And also one thing to keep in mind from a performance or memory consumption perspective is that when you have upsampling, you have duplication of data, which means that you have bloating of your data set. So you start with a big data set, and then you have an even bigger data set at the end. So this is why we provide the second option, which is in a pull request right now, so it's pending, but it's going to be available very soon. So this is the index preserving approach that I've shown in the second example. And same thing, we pass a custom aggregation function to tell the algorithm what to do when there are multiple values that are being condensed into one. So I'm going to go over the API quickly. So those are the high-level objects that you'll be interacting with as a user of the library. The first one, and probably the most important one, is the time series RDD object, which is our distributed multivariate time series. Then we have time series, which is a locally collected version of that time series RDD, on which you can perform the same kind of operations that you can on the time series RDD. We have some statistical tests, like autocorrelation tests and things like that. We have some standard time series forecasting models, nothing too fancy. We have the datetime index object, which we've already talked about. And we have some utility functions for univariate vectors of data. So what can we do on these time series RDD objects? Well, we can collect them as local time series. We can slice them in time, so take subsets of that time series. We can filter out some instance in time based on a custom filtering function. We can take quotients, differences, lags. We can fill in missing values using pre-specified interpolation methods. We can obtain summary statistics like min, max, average, standard deviation. We can transform to row-based representation, as we've talked about, with two-instance or two-instance data frame. We can perform resampling operations, as we've also talked about. There's the rolling sum and rolling mean operations. And we can save to and load from CSV and Parquet file formats. So these are some of the statistical tests that we support. We have stationarity tests, augmented Dickey-Fuller, and KPSS. We have serial autocorrelation tests, Durbin-Watson, Broich-Godfrey, and Young-Box. We have the Broich-Pagan heteroscedasticity test, and we have the Newey-West variance estimator. Some of the time series models that we support, we have autoregressive, ARIMA, autoregressive and ARIMA with exogenous variables. We have exponentially weighted moving average models. We have the Holt-Winters method, which I will explain in the second code example. And we have some special cases of the conditional heteroscedasticity models. So the library was written in Scala natively, but if you're a Java programmer or Python programmer, we have bindings also for that. Okay, so first code example. Let's say that we have this data set composed of two variables, y and x. And here I only show the 5 oldest values, but you can assume that there's a lot more of those values. And let's further say that y is stationary and x is non-stationary. So what we're going to do is we're going to take that example, pre-process it in a similar way as the time series regression formula that we've showed earlier. We're going to take the first 2 lags, and we're going to use the first 2 lags to predict the variable y. We're also going to check if any of those are non-stationary and transform them to stationary to avoid spurious regression. And then we're going to pass this resulting data set to MLlib's lasso regression API. And this is how we do it. So I'm going to go line by line. The first line, well, we simply load our data set into a time series RDD from a CSV file. I have to say that currently our CSV files have to be of a very specific format. We don't have flexibility into what the format can be like. This is something hopefully we will work on later. In the second line, what we do is we slice off the oldest values. And the reason we do that is that we're going to be taking the first difference of some of these vectors. And when you take the difference, well, you have to get back to the previous value, and the oldest value do not have any value before them to take the difference. So these values become unusable. So we slice them off. And then I call map series on the time series RDD. Map series is simply a way to apply a certain closure to every single vector in our time series RDD. And in this case, the code that we apply to every column is first, we run the augmented Dickey-Fuller test on them to determine if they are stationary or non-stationary. And if they are non-stationary, so if the p-value is greater than 0.05, we take the first difference of that to obtain a stationary time series. Once we've done that, we call .lags to obtain the first 2 lags of this time series. And also I specify a map after that. So this map parameter is there to indicate for which variables do we keep the original non-lag values. And the reason we keep the original non-lag value for y is because this is the variable that we're going to predict. So we need to have the values at time t, but we're going to predict that value as a function of the variables at time t-1 and t-2. So we keep the y, the original, but we get rid of the other originals. And then once we're done with this pre-processing, we simply transform it to row representation with .toInstance, and we map it to a label point, and then we're ready to call the MLlib API, so in this case, the lasso regression model. And this fits our model. Here I show the result of the pre-processing that we do with Spark time series. So in gray are the values that are removed, and we see that we take the first differential of x, which is what the d parenthesis x stands for, and we take the first 2 lags of the variables. We also get rid of the non-lagged differential of x for the reasons I just explained. And also the first 3 rows, the oldest 3 rows of data, they get removed because of the lagging and differencing that we applied made some of these values unusable. Okay, second and last code example. Here we're using the Holt-Winters method. So the Holt-Winters method is good for seasonal data. And the way it works, it is based on the concept of exponential moving averages. We apply the exponential moving average to the levels of the variable, to the trend of the variable, and to the seasonal cycle of the variable. And with these three independent exponential moving average models, we then forecast the level at time t plus 1, we forecast the trend at time t plus 1, and we forecast the seasonal effect at time t plus 1. And then finally, we combine these three forecasts into a global forecast. We're going to apply this forecasting model to monthly airline passengers data. And what we see in the obvious cycles that we have in this data, this is about a year of data. So this is what the code looks like. So we call Holt-Winters.fit model. We pass the time series data. We specify that our cycle is a year, so 12 months. And we specify the variance. So without going into mathematical detail of this, there are two variants of the Holt-Winters method. There's the additive and multiplicative variant. And here in this example, we actually train both variants and we compare the results. And the last model is the optimization algorithm that is used to fit the Holt-Winters method internally. After that, what we do is simply allocate a vector of 12 placeholders, 12 values, because we're going to forecast the next 12 months with this model. And we call .forecast to produce these 12 forecasts. And this is, by the way, an out-of-sample forecast. And this is the result that we get. So in blue is the actual next 12 months in the data. In purple is the additive forecast for the next 12 months. And in red is the multiplicative forecast for these next 12 months. So we can see that Holt-Winters performs pretty well for these kinds of strongly seasonal data sets. And that's the end of my presentation. If you have any questions, you can send me an email at that address. And we're hiring at Fame Data. We're a consumer intelligence company in Montreal, Canada. We're looking for data scientists, Spark engineers, machine vision specialists. So if you're curious about those positions, you can also email me at that address. Thank you.
We have about 8 minutes for questions, if there are any.
Do you have the plans to integrate with data frames and data sets, Spark streaming?
Sorry?
Integrate this library with data frames,
yes.
Data sets, and Spark streaming?
Yes. Spark streaming, no. There's anything that's specifically related to Spark streaming at the moment. But I can show there's this, if you look at the two-instance and two-instance data frame, so once we've done the pre-processing with the time series, we can transform it to a data frame that is row-based, and then from there you can use any library that works on a data frame.
Hi. I saw that you said you use Scala and Python. Are you also thinking about R in the future?
Well, we haven't talked much about R, but that's something that, I mean, it's an open source, it's an open source project with a lot of individuals collaborating, so you never know what's going to happen. If somebody has a need for this R integration, it might happen, but we haven't necessarily talked about that yet, no.
Okay, if there are no more questions, that's. I'm sorry, there are more questions. Okay. Excuse me.
Just curious, is this going to be posted online somewhere, your slides?
Yes, I believe that all of the slides will be posted online, I think.
Because I know they are recorded. I know their video is recorded.
No, I think the slides are made available as well, yeah.
Do you agree with the previous speaker about the difference between Flint and this?
He was right about the limitations that I've talked about here. So here, because our partitioning is columnar, well, there's a limit to how much data you can contain right now. So he was totally right about that, and I noticed that in Flint, the representation is row-based, if I did not misunderstand. So that limitation is removed. This is also something that we wanted to add in the future, we'll see. But he also mentioned that it was supporting only uniform, but that is not the case. We also support irregular.
I have a very basic question. Is there any plan to support SQL? Like, if we have a lot of SQL experts, but they use a lot of, do a lot of time series processing. So
Right. So you mean loading the data from a SQL database as opposed to a CSV file, for example? Is that the question?
no. I meant like actually writing SQL instead of having to write a bunch of code to process.
That's a good question. I haven't really thought about that, to be honest.
Okay, I'm not seeing any more hands, so that wraps it up for this talk. The next talk will begin at 12:20. Thank you.